Chapter 8. Neural Network Optimization and Efficiency. 8.1 Advanced Optimization Algorithms for Neural Networks. Optimization algorithms are essential for training neural networks. They adjust the weights of connections in the network to minimize a loss function, which measures the difference between the predicted output and the actual output. The choice of algorithm can have a significant impact on the speed and quality of the training process. In the early days, gradient descent was the key workhorse, but it has since been superseded by more advanced and efficient techniques that are the focus of this section. Stochastic gradient descent, SGD, is a foundational algorithm that introduced randomness in selecting data points to update weights, allowing for faster convergence than standard gradient descent. However, SGD does not guarantee the optimal path towards the minimum of the loss function. As such, several improvements have been proposed. One of the crucial improvements is the introduction of momentum. SGD with momentum retains a fraction of the previous update direction, thereby gaining speed along dimensions where the gradient consistently points in the same direction and reducing oscillations in dimensions where the gradient changes rapidly. Adaptive learning rate algorithms provide another significant enhancement over basic SGD. These algorithms, such as ADAGRAD, ADADelta, and RMSProp, adjust the learning rate dynamically based on the historical gradient information of each weight. ADAGRAD, for example, scales the learning rate inversely proportional to the square root of the sum of all past squared gradients. Although ADAGRAD can dramatically improve the performance of SGD, especially in scenarios with sparse data, it has a fundamental drawback. As the sum accumulates, the learning rate continually decreases and eventually becomes infinitesimally small, hindering further improvement after a certain point. To overcome the limitations of ADAGRAD, the ATOM optimization algorithm was introduced. ATOM, which stands for Adaptive Moment Estimation, combines the benefits of adaptive learning rate algorithms and momentum. It maintains a moving average of the gradients and their squares, which are used to adjust the learning rates. Because it calculates adaptive learning rates for each parameter, ATOM generally converges faster than other variants. Furthermore, it is less sensitive to the initial learning rate setting, making it a go-to choice for many deep learning practitioners. Another notable algorithm is the Nesterov Accelerated Gradient, NAG. It improves upon the concept of momentum by calculating the gradient not at the current parameters, but at the approximate future position of the parameters. This foresight allows for more informed updates, leading to faster convergence and reduced overshooting during training. It is particularly effective in situations where the loss surface is not well conditioned, or where S-curves are pronounced. While these algorithms advance the efficiency of optimization, they still operate under the auspice of first-order optimization. That is, they only leverage the first derivative, gradient, of the loss function. Second-order optimization methods, such as those utilizing the Hessian matrix or its approximations, have also been developed. Nevertheless, because of their computational complexity, the Hessian matrix contains second-order derivatives and is often very large. They are not commonly used in practice for large-scale neural network training. Recent developments have also seen the use of meta-heuristic algorithms such as genetic algorithms, GAS, and particle swarm optimization, PASEO, for neural network training. These algorithms simulate natural processes and have a stochastic nature. For instance, GAS mimic the process of natural selection where the fittest individuals are selected for reproduction in order to produce offspring of the next generation. In the context of neural networks, individuals could represent different sets of weights, and fitness would correspond to high accuracy or low loss. Although these methods can be computationally expensive and do not guarantee to find the global minimum, they have been effective in escaping local minima and finding satisfactory solutions in complex landscapes where traditional gradient-based optimizers struggle. In distributed and large-scale training environments, the use of advanced optimization algorithms becomes even more important. Techniques like asynchronous SGD or federated learning algorithms allow for neural networks to be trained across multiple machines or even across a network of devices, such as mobile phones. These approaches are designed to handle the increased computational load and data volume, and have been pivotal in training state-of-the-art models that are too large for a single machine. Furthermore, the advancement in hardware accelerators like GPUs, TPUs, and custom ASICs has dramatically changed the landscape of neural network optimization. Hardware-specific optimizations can offer speed-ups by parallelizing computations, taking advantage of specialized architectures, and optimizing memory usage. Algorithm hardware co-optimization is a burgeoning field that seeks to design neural network optimization algorithms that complement the strengths of the hardware on which they run, achieving further efficiency gains. All the advanced optimization algorithms discussed contribute to the main goal, reducing the training time of neural networks without compromising the accuracy. However, there is no one-size-fits-all solution, and a practitioner's choice of algorithm often depends on the specific problem, the size of the dataset, and the architecture of the neural network. As the research continues to evolve, new techniques are developed continually, and existing methods are refined to train deeper, more complex neural networks more efficiently. It is an area that represents a fruitful intersection of applied mathematics, computer science, and practical engineering, all aimed at enabling neural networks to learn as effectively as possible. 8.2 Efficient Training Techniques. Efficient training of neural networks is of paramount importance for practical applications. It ensures that the computational resources are aptly utilized without wastage while achieving the desired performance metrics. Effective training techniques can bring significant improvements in terms of training time, memory utilization, and energy consumption. In the era of big data and complex models, these considerations become crucial for scalability and sustainability. Optimization techniques, data pre-processing strategies, and architectural modifications all play a role in efficient neural network training. The first technique to improve neural network training efficiency is data normalization. By scaling input features to a common scale, the network's responsiveness to feature discrepancies is normalized. This can address issues wherein certain features dominate the training process due to their larger scale, leading to imbalance and inefficiency. Data normalization accelerates convergence by adjusting the landscape of the optimization problem to be more isotropic. Techniques such as z-score normalization or min-max scaling are often applied to input data before commencing the training process. Another critical aspect of effective training is weight initialization. Proper initialization strategies prevent saturation of the neural network's activation functions early in the training phase. This saturation can lead to vanishing or exploding gradients, impeding the network's learning capacity. Modern initialization methods such as He initialization or Xavier initialization ensure that the weights are set to values that favor an efficient training process. By maintaining a variance that is conducive to learning across deep networks, these techniques enable faster convergence and a more stable training phase. Mini-batch gradient descent is an optimization technique that balances the computational benefits of stochastic gradient descent with the stability of batch gradient descent. By processing a subset of the dataset at a time, the model updates are both more frequent than a full batch update, and less noisy than individual sample updates. Mini-batch sizes are a hyperparameter that must be configured carefully, considering memory constraints and the noise level that the training process can tolerate. It is a compromise that allows efficient use of hardware resources while maintaining steady convergence patterns. Regularization is a concept employed to improve training efficiency by discouraging complexity in neural network models. Methods such as L1 and L2 regularization add penalty terms to the loss function, which are functions of the magnitude of the network's weights. These penalties compel the network to keep the weights low, unless high values are justified by a significant improvement in data fit. This simplification process leads to models that generalize better to unseen data and require less computational power for training. Additionally, dropout is a form of regularization that randomly deactivates nodes during training, which encourages the network to develop a more robust representation of the data rather than relying on any single node. Learning rate scheduling adjusts the learning rate over the course of training, which can significantly affect training efficiency. A high learning rate might converge quickly but can overshoot minima, while a low learning rate might be precise but converge slowly. Adaptive learning rate algorithms, such as ADAM or RMSPROP, automatically adjust the learning rate based on the update history of each weight. This intelligent scaling down of the learning rate as the training progresses allows for quick initial progress with gradual refinement, enhancing training efficiency. Transfer learning is a training acceleration technique which takes a pre-trained network and fine-tunes it on a new, but similar task. This is an efficient approach because the initial layers of a neural network often capture universal features that are not specific to a particular task, like edges or textures in image processing. By reusing these pre-trained layers, the network requires fewer epochs to converge, saving time and computational resources. Transfer learning has risen to prominence, especially in domains where labeled data is scarce or expensive to obtain. Efficient neural architecture search (NAS) algorithms seek to find optimal network architecture for a given task. Traditional NAS methods are computationally expensive because they require training hundreds or thousands of candidate structures. Recently, efficient NAS strategies such as weight sharing or one-shot NAS have been developed. These methods reduce computation by sharing weights across different architectures or by approximating network performance instead of fully training each candidate, which accelerates the discovery of efficient architectures. A technique often overlooked in the realm of neural network efficiency is the precision of data representation. In many cases, training can be done using lower precision arithmetic without significantly affecting performance. This approach, broadly termed as mixed precision training, exploits the capability of modern GPUs that can operate more rapidly with half-precision floating point numbers. By reducing the precision, not only does the speed of matrix multiplications and other arithmetic improve, memory usage also declines, allowing larger models or batch sizes to fit into the same GPU memory. Batch normalization is another commonly used technique to enhance training efficacy. It normalizes the input of each layer so that the mean activation is close to 0 and the standard deviation is close to 1. This stabilization of the distribution of activations helps alleviate issues like the internal covariate shift. With batch normalization, networks train faster and have the fortitude to use higher learning rates, as the problem of exploding gradients is mitigated. As a result, batch normalization can generate more efficient training cycles and can also lead to better overall performance. Finally, optimization for efficiency also means considering the algorithmic complexity of neural network operations. Sparse representations in computations can sometimes replace dense matrices without sacrificing model accuracy. Sparse matrices only store and compute non-zero elements, which can offer significant computational savings when dealing with large and sparse datasets. Moreover, model pruning techniques aim to reduce the network size after training by eliminating weights that contribute minimally to the output. Not only does this save memory and computational resources during inference, but often, retraining a pruned model can lead to more efficient computation during subsequent training iterations. These techniques illustrate the spectrum of strategies that can be employed for efficient training of neural networks. While no technique is universally best, their judicious application can lead to substantial improvements in training time and resource utilization. Such efficiency considerations become increasingly consequential when scaling up to larger datasets and more complex models. Effective training techniques, therefore, represent a balance between exploiting computational resources and achieving a rapid learning process without compromising the capacity or accuracy of the neural network. 8.3 Pruning and quantization for model compression. Deep neural networks have demonstrated remarkable effectiveness in various complex tasks, from image recognition to natural language processing. However, their deployment on devices with limited computational resources, such as mobile phones or embedded systems, can be challenging due to their large size and heavy computational requirements. Model compression techniques, namely pruning and quantization, are critical for improving the efficiency of neural networks without significantly sacrificing accuracy. Pruning is a method of reducing the size of a neural network by eliminating weights that contribute little to the output. It effectively reduces the complexity of a model by removing the connections between neurons in the network that are deemed unnecessary. This technique relies on the premise that some weights, especially those with very small magnitudes, have a minimal impact on the performance of the model. Pruning can be performed at various levels of granularity, ranging from individual weights to entire neurons or layers. The pruning process typically begins with the training of a larger, over-parameterized network that is expected to have redundant weights. After training, a pruning criterion is applied to identify the dispensable connections within the network. This criterion can vary, with some methods focusing on the magnitude of weights, while others consider the gradients or other salient features. Once the superfluous weights are identified, they are set to 0, effectively removing them from the network. The pruned network then undergoes a fine-tuning process to recover any lost accuracy resulting from the pruning step. Quantization, on the other hand, refers to the process of reducing the precision of the weights and activations of a neural network. By default, neural networks often use 32-bit floating-point numbers for representing weights and neuron activations. Quantization involves converting these high-precision representations to lower bit width formats, such as 16-bit integers or even smaller, which can accelerate inference and reduce memory usage significantly. There are varying approaches to quantization, including post-training quantization and quantization-aware training. Post-training quantization applies quantization after the model has been fully trained, while quantization-aware training incorporates quantization into the training process itself. The latter tends to yield higher accuracy, since the model has the opportunity to learn and adapt to the reduced precision weights during training. The key challenge in quantization is to strike a balance between model size and computational efficiency, on one side, and the model's accuracy on the other. Lower bit width representation reduces the model size and speeds up computation, but it may also lead to a degradation in performance if not done carefully. Various quantization schemes are employed, such as uniform quantization, where the range between the minimum and maximum value is divided uniformly, and non-uniform quantization, which can assign more fine-grained representations to more frequent values. In practice, pruning and quantization can be used separately or combined to achieve significant model compression. When combined, the process usually entails first pruning the network and then applying quantization on the sparser structure. This sequential approach is often effective, as pruning may expose additional redundancy that can be effectively handled by quantization, further reducing the model's footprint without a substantial impact on accuracy. Another significant aspect of model compression is the deployment of the resulting compact neural networks. The real-world effectiveness of compressed models depends not only on their reduced size, but also on the compatibility with the hardware they are deployed on. Hardware-accelerated inference engines, for example, can benefit considerably from models that have been quantized to lower precision, as they can exploit specialized instruction sets optimized for low-precision arithmetic. Moreover, different platforms might have varying support for sparsity induced by pruning. Some hardware accelerators are designed to skip zero-valued weights efficiently, while others may not have this capability. It is crucial for practitioners to be aware of these hardware-specific characteristics when opting for pruning, quantization, or both. This ensures that the compressed models not only have a reduced size, but are also optimized for the target hardware, enabling faster and more energy-efficient inference. When implementing pruning and quantization, it's important to consider the end application of the neural network. Tasks with inherently lower tolerance for errors, such as medical image analysis, might require a more conservative approach to compression to maintain high accuracy. In contrast, applications such as mobile apps or consumer electronics can often afford a slight drop in precision for the benefit of reduced model size and faster performance. Maintaining model accuracy after compression remains a central concern in neural network optimization. Researchers and engineers continue to develop more sophisticated pruning algorithms and quantization techniques that aim to compress neural networks with minimal loss in accuracy. These methods often involve iterative processes that incrementally prune or quantize the network, interspersed with retraining or fine-tuning steps to regain lost performance. The field of neural network optimization and efficiency is dynamic and evolving. As new architectures and hardware platforms emerge, the strategies for pruning and quantization have to adapt accordingly. Recent advancements include automated machine learning, AutoML frameworks that can help in finding the best model compression strategies for a given task, and hardware-aware neural network design that integrates model optimization directly within the architecture search process. Through rigorous empirical evaluation, these model compression techniques have demonstrated significant improvements in the speed and efficiency of neural networks across a variety of tasks and platforms. The continued refinement of pruning and quantization methods promises to expand the applicability and impact of neural networks, allowing them to run seamlessly on devices at the edge of computing and beyond. As the demand for efficient AI solutions grows, the importance of model compression through methods like pruning and quantization will undoubtedly increase, opening up new frontiers in accessible and sustainable AI deployment. 8.4 Distillation for neural network training. The concept of distillation for neural network training finds its roots in the transfer of knowledge from a comprehensive, often unwieldy model, known as the teacher, to a smaller, more efficient model, the student. This process is critical in scenarios where computational resources are limited or where deployment environments cannot accommodate the larger model's size and complexity. The distillation technique revolves around the idea of capturing the representational power of the teacher network and transferring it to a student network, which is designed to be less computationally intensive. It is particularly useful when there is a need to deploy sophisticated neural network capabilities on devices with constrained resources, such as mobile phones, embedded systems, or other portable devices. To begin the distillation process, the teacher network, which has already been trained on a comprehensive dataset, generates soft targets. Soft targets are essentially the outputs of the teacher network, often in the form of probability distributions rather than hard labels. These soft targets contain richer information about the input data as compared to hard labels, including insights on the relative probabilities assigned to incorrect classes. They express the teacher model's confidence about its predictions and reveal interclass relationships that a hard maximum output would obscure. The student model is then trained not just to predict the correct label, but to mimic the probability distribution produced by the teacher model. By doing so, the student network can learn the nuanced relationships that the teacher perceives between different classes and the finer representations of the input data. Training the student model involves a delicate balance of learning from the soft targets provided by the teacher and adhering to the true labels of the dataset. This is often achieved by constructing a loss function that incorporates both cross-entropy with respect to the true labels and a term reflecting divergence from the teacher's soft targets. The latter is frequently measured by Kullback-Leibler divergence, a statistical method used to quantify the difference between two probability distributions. The overall loss function thus becomes a weighted sum of these two terms. During training, the student model updates its weights not only to minimize its error on the training set, but also to align closely with the teacher model's predictions. The architecture of the student network is a deciding factor in the success of distillation. It must be carefully tailored to ensure that the capacity is sufficient to encapsulate the teacher's knowledge. However, the student network should remain light enough to offer the desired computational benefits. If the student network is too simple in structure, it will lack the capability to approximate the function learned by the teacher. Alternatively, if it is too complex, the benefits of distillation in terms of efficiency may be negated. Therefore, the design of the student network is typically an exercise in compromise, balancing model complexity against the desired efficiency gains. Once the student model is trained and deployed, it can provide predictions that are often comparable to those of the teacher model, but with significantly reduced computation and storage requirements. The impact of this can be seen in various applications. For instance, in natural language processing and computer vision, substantial models are used to achieve state-of-the-art results, but they are not always deployable on end-user devices. Through distillation, many of these capabilities can be transmitted to practical, deployable models without a substantial sacrifice in performance. One notable evolution of the distillation concept is the introduction of intermediate representations as additional sources of knowledge transfer. Advanced teacher models often learn useful representations at various hidden layers, not just at the output layer. By aligning the student's intermediate layers to these learned representations, more of the teacher's knowledge can be transferred. This variation of distillation is sometimes called hint-based training, where the teacher provides hints to help guide the student's learning process. These hints come in the form of feature maps or activations from selected layers within the teacher network, providing additional targets for the student to learn during training. However, there are challenges and considerations associated with neural network distillation. One issue is the potential mismatch in capacity between the teacher and student models. If the disparity is too great, the student might not be able to learn effectively from the teacher, resulting in a reduction in performance. Another challenge arises when there are discrepancies between the training and deployment environments. These discrepancies could be due to differences in data distribution, computational limitations, or quantization effects, which can affect the student's performance. Care must be taken when designing distillation training regimes to ensure that the student model is robust to such shifts in environment. Distillation also opens up questions about the transferability of adversarial robustness from teacher to student models. In the context of adversarial machine learning, where models may be subjected to malicious inputs designed to cause them to fail, it is not yet fully clear how effectively a teacher's robustness against such attacks can be taught to a student. Early research suggests that while some level of robustness can indeed be transferred through distillation, the complexities of adversarial training require specialized strategies to maintain this aspect of model performance. Looking ahead, there are emerging opportunities to improve and expand the concept of distillation, which includes automated processes for student architecture selection and hyperparameter tuning of the distillation loss function. These advancements have the potential to enhance the efficiency and performance of the student model, narrowing the gap between it and the teacher network even further. Moreover, with the advancement in unsupervised and semi-supervised learning, there is active exploration into how distillation might adapt to leverage and label data more effectively. In a broader sense, distillation for neural network training is a concrete example of how the machine learning community addresses practical deployment challenges. It demonstrates a commitment to not only advancing the theoretical frontiers of model capacity and performance, but also to ensuring that these advancements are accessible and applicable in real-world scenarios where constraints are unavoidable. As computational demands continue to grow, distillation and analogous techniques will likely play a crucial role in making powerful neural networks broadly deployable and sustainable. 8.5 Hardware acceleration for neural networks. Hardware acceleration for neural networks refers to the use of specialized hardware to speed up the processing of neural network algorithms. Typical processors such as standard central processing units, CPUs, are not optimized for the parallel processing requirements of neural networks. CPUs are built for a wide range of tasks and, while versatile, do not excel at the kind of high-throughput matrix-focused computations that neural networks demand. In contrast, hardware accelerators are designed to perform these specific computations more efficiently, thus reducing both the training and inference times of neural networks. Graphics processing units, GPUs, are the most common form of hardware acceleration for neural networks. Originally designed to handle the rendering of graphics for gaming and other visual tasks, GPUs have a large number of cores that can perform calculations simultaneously. This makes them highly suitable for matrix and vector operations that are central to neural network processing. GPUs provide a significant increase in speed compared to CPUs for both the training and deployment of neural networks, allowing for more complex models and faster iteration. Another form of hardware acceleration is the use of field programmable gate arrays, FPGAs. FPGAs are integrated circuits that can be configured by the customer or designer after manufacturing, hence, field programmable. They are used in a variety of applications requiring specific processing capabilities. For neural networks, FPGAs can be programmed to perform the required linear algebra operations very fast. Although they generally offer lower peak performance than GPUs, FPGAs can be more energy efficient and can be customized for the needs of a particular neural network, which can lead to higher overall performance in some cases. The emergence of specialized accelerators, known as tensor processing units, TPUs, marks another step toward more efficient neural network computation. Developed by Google for their own use in data centers, TPUs are application-specific integrated circuits, ASICs, designed specifically for tensor computations, which are the core operations in neural network processing. They provide performance levels that can exceed those of both GPUs and FPGAs, particularly in large-scale deployment scenarios. TPUs are tailored to run TensorFlow, Google's open-source machine learning framework, underscoring the move towards specialized hardware in the machine learning space. Optimizing neural network performance also requires consideration of memory bandwidth and latency. The efficiency of a hardware accelerator can be significantly compromised if the movement of data between the processing units and memory is a bottleneck. High-performance accelerators come with high-bandwidth memory, HBM, or similar technologies that ensure a fast and wide pipeline for data transfer, helping to maintain high utilization of the computation cores. Interconnections between hardware accelerators are equally important, especially in distributed neural network training scenarios. Technologies such as NVIDIA's NVLink or AMD's Infinity Fabric can provide high bandwidth and low latency connections between GPUs. This connectivity is crucial when scaling up training to multiple GPU instances, as it allows for rapid exchange of data, such as model parameters and gradients, which helps reduce synchronization overhead. The advancement of hardware accelerators also comes with the need for specialized software to effectively harness their power. Libraries and frameworks such as CUDA for NVIDIA GPUs or OpenCL for general-purpose computing on heterogeneous systems are essential. They provide the tools and resources developers need to optimize neural network models for accelerated hardware. Profiling and optimization tools help developers understand where bottlenecks lie and how to adjust computations to fully utilize the hardware's capabilities. Energy efficiency has become an increasingly important consideration in the design of hardware accelerators. As neural networks grow in complexity and size, the power required to train and run them also increases. This is particularly relevant for deployment in environments where power consumption is a critical factor, such as mobile devices or data centers. Many accelerators are now designed with power efficiency in mind, striking a balance between computational performance and energy use. In addition to these general-purpose accelerators, there is also growing research and development in neuromorphic computing. This field seeks to mimic the neural structures of the human brain in hardware, resulting in systems that can potentially run neural network models with a fraction of the power consumption of conventional hardware. Neuromorphic chips, while still largely experimental, could one day provide a new paradigm for efficient neural network computation. Overall, the landscape of hardware acceleration for neural networks is diverse and rapidly evolving. Each type of hardware accelerator offers its own balance of computational performance, energy efficiency, and suitability to different tasks in neural network structures. The choice of hardware can significantly impact the speed and effectiveness of training and deploying neural networks. As the demand for AI applications grows, continued innovation in hardware acceleration is crucial for supporting the increasing complexity and scale of neural network models. Robust, efficient accelerators are key to unlocking the full potential of neural networks in a wide array of uses, from consumer applications to scientific research. 8.6 Neural network deployment on different platforms. Deploying neural networks effectively across different platforms requires a keen understanding of both the neural network model architecture and the underlying hardware capabilities of the deployment target. Various platforms such as mobile devices, embedded systems, cloud servers, and high-performance computing clusters each come with distinct characteristics and constraints. For instance, mobile devices and embedded systems are often limited by processing power, memory, energy usage, and thermal constraints, making it imperative that neural network models are optimized for efficiency on these platforms. On the other hand, cloud servers and high-performance computing clusters typically offer more memory and processing power, enabling them to handle larger, more complex models. Still, deployment on these platforms involves considerations around network latency, data throughput, and cost of computation at scale. The software ecosystem of the target platform also affects deployment strategies. Different platforms might necessitate different neural network frameworks or libraries, which in turn could restrict or enable certain optimizations and influence the choice of training and inference protocols. A core consideration in deploying neural networks is the conversion of the training model to an inference model. The training phase is characterized by iterative updates to the model parameters, extensive data shuffling, and backpropagation of errors to facilitate learning. Upon completion of training, the neural network is typically frozen, meaning its weights and biases are no longer updated, and it is stripped of components only necessary for training, such as dropout layers and auxiliary outputs, to streamline the model for inference tasks. This process can reduce the model's size and computational demands, enhancing its performance during deployment without degrading accuracy. Model quantization is another crucial optimization step. It converts the high-precision weights of a trained neural network, often 32 or 64 bits floating point values, to lower precision representations, such as 16 bits floats or even 8 bits integers. Lower precision arithmetic significantly decreases memory usage and accelerates computation since the simpler operations can take advantage of hardware optimizations, particularly on mobile devices equipped with processors that have dedicated instruction sets for fast, low-precision arithmetic. Beyond optimizing the model itself, it is essential to consider data serialization formats and communication protocols needed for deployment. For example, in scenarios where a neural network is deployed on a mobile device, but actual inference takes place on a cloud server, the communication protocol should be secure and efficient to handle large volumes of data with minimal latency. Protocols like gRPC or efficient data serialization formats like protocol buffers can be used to exchange inference data between the client device and the server in a compact and efficient manner amidst the various constraints of network bandwidth and latency. Moreover, when deploying neural networks to different platforms, the model may need to interface with other software components or application programming interfaces, APIs. In such cases, the neural network should be encapsulated within a larger service or application in a way that promotes modularity and ease of maintenance. This often implies the creation of a clean API around the neural network model, which abstracts away the complexities of direct model interaction and provides a simple interface for data input and output. While deploying neural networks to low-power devices like those in the Internet of Things, IoT environments, edge computing becomes a significant factor. Edge computing pushes computation away from centralized data centers to the edges of the network, closer to data sources. Deploying neural networks to edge devices allows for real-time data processing and decision-making, reducing the need to transmit large volumes of raw data to centralized locations for analysis. However, this introduces challenges related to model size and operational latency, because edge devices often lack the computational resources of larger systems. In certain usage scenarios, neural networks must be able to learn and adapt post-deployment, leading to the concept of continual learning or lifelong learning systems. In such cases, the deployment framework must support and manage periodic model updates without interrupting service. It should also ensure that new data used for learning does not lead to catastrophic forgetting of previously learned knowledge. This requirement makes the management of model updates, particularly in distributed systems, a non-trivial task that should be thoughtfully designed to maintain model performance and stability over time. Finally, the deployment of neural networks on different platforms must conform to various security and privacy considerations. Ensuring that the model does not become a vector for data breaches or exploitation is paramount. The confidentiality and integrity of the data processed by the neural network must be upheld, particularly in privacy-sensitive applications. This implies that robust security practices, coupled with encryption of data in transit and adherence to principles of least privilege in system design, become vital components of any deployment strategy. The neural network deployment process is iterative and often involves monitoring, measuring performance, and making necessary adjustments to the model or the deployment environment. Dedicated tools and services have been developed to facilitate this lifecycle, automated pipelines that perform model conversion, deployment, and monitoring. This ecosystem of tools and services enables developers to manage the nuanced differences between deployment platforms efficiently and to keep their models operating at optimal levels, satisfying the different demands of modern computational environments. 8.7 Scalability Challenges and Solutions. Scalability in neural networks is a multidimensional challenge that includes model size, data size, complexity of operations, and the requirement to decrease training and inference times while maintaining or improving performance. As datasets and network architectures grow, the demand for computational resources increases significantly. State-of-the-art neural networks often require extensive computational power, which can be costly and energy-intensive. Managing these scalability challenges is crucial for the practical application of neural networks in large-scale and real-time environments. One fundamental scalability issue involves the size of the neural network models. Larger models with millions or even billions of parameters can capture complex patterns and perform better on tasks such as language translation, image classification, and voice recognition. However, as model size increases, so does the need for memory and processing power. This creates a barrier to entry for organizations and researchers without access to high-performance computing systems. To address this, techniques like model pruning, which removes non-critical neurons and connections, and knowledge distillation, where a smaller student network is trained to replicate the performance of a larger teacher network, can be utilized to reduce model size while retaining performance. Data scalability is another significant challenge. As datasets grow, they can take longer to process, requiring more storage and bandwidth to handle the data influx. Techniques such as data parallelism distribute the data across multiple processing units, typically GPUs or TPUs, to tackle the large dataset issue. Each unit processes a subset of data, and the updates are consolidated to update the model parameters. However, efficient distribution of data and synchronization of model updates can be complex and may introduce communication overhead, which leads to additional challenges. Another scalability issue is the time required for training and inference. Training larger models on larger datasets can take days, weeks, or even months, which is not feasible for applications requiring rapid development cycles or real-time analysis. Optimizing the computations performed during training and inference, such as by using mixed precision arithmetic, can speed up the process without sacrificing much accuracy. Mixed precision training uses both single and half-precision floats, where the latter requires less memory and computational power to perform calculations more quickly. The complexity of neural network operations also poses challenges to scalability. Operations such as convolutions in convolutional neural networks, CNNs, or the attention mechanism in transformer models are computationally intensive. Optimizing these operations through the use of specialized hardware accelerators like FPGAs or ASICs can provide significant speedups. These devices are designed to perform specific types of calculations more efficiently than general-purpose CPUs or GPUs. Furthermore, the drive towards real-time inference poses additional scalability challenges. Many applications, such as autonomous driving or medical diagnostics, require the model to process and interpret data in real time. To reduce latency, model deployment on edge devices or the use of quantization, which converts high-precision weights to lower-bit representations, are common solutions. These methods help to decrease the model size and increase the speed of inference, making it more suitable for real-time applications. The energy consumption of neural networks is also a growing concern as models scale. The computational resources required to train and run large neural networks can result in a substantial carbon footprint. More energy-efficient network designs, improved data center energy utilization, and a shift towards renewable energy sources for computation can help mitigate these environmental impacts. Reinforcement learning and neural architecture search are promising methods for specifying more energy-efficient network architectures that do not compromise on performance. Maintenance and continual learning present additional scalability challenges. Neural networks require regular updates and maintenance to stay relevant as new data becomes available. Continual learning involves updating the model with new data without forgetting previously learned information, which is a non-trivial task, especially for large-scale networks. Methods like elasticity scaling that dynamically add or remove resources based on demand and progressive neural networks that can add new knowledge while retaining previously learned information are among the approaches used to maintain neural network efficiency. Distributed training and federated learning are growing trends aimed at addressing scalability challenges. Distributed training involves training the same model in parallel across multiple machines, whereas federated learning trains algorithms across decentralized devices holding local data samples. These approaches help in scaling out neural networks by leveraging a larger number of computation nodes, but introduce challenges such as dealing with non-IID data distribution, communication overhead, and maintaining privacy and security. Lastly, the software and frameworks used to develop and train neural networks influence scalability. Tools such as TensorFlow and PyTorch have matured significantly, offering distributed training capabilities, but optimizing these tools for specific hardware or use cases can be intricate. Innovations in software frameworks that provide more efficient utilization of hardware resources, easier distribution of computation, and simplified parallel processing will continue to be essential in overcoming neural network scalability challenges. However, the industry continues to innovate, seeking to balance the trade-offs between model capacity, efficiency, and the feasibility of scaling to meet the demands of an ever-growing range of applications. This includes exploring new paradigms for neural network design, training techniques, and hardware-software co-design, which will be critical for ensuring the sustainable scalability of neural networks in years to come. As we proceed, staying apprised of these developments is imperative for anyone in the field of machine learning and artificial intelligence. 8.8 Energy and Resource Efficient Neural Network Design. Neural network efficiency is a critical factor in the deployment of machine learning models in various applications. Energy and resource-efficient neural network design aims to minimize the computational resources required for training and inference while maintaining, or in some cases even enhancing, the performance of the model. This is significant in an era where the environmental impact of computing is under scrutiny, and computational resources are finite. The need for efficient neural networks arises from several factors. First, the computational demands of state-of-the-art models are growing exponentially, and training these models can consume a substantial amount of electricity, contributing to high operational costs and carbon emissions. Second, efficient models are vital for deployment on edge devices, like smartphones and embedded systems, which have limited computational capacity and power availability. Consequently, the focus on designing energy-efficient neural networks aligns with sustainability goals and extends the applicability of machine learning technologies. One approach to designing more efficient neural networks is through the implementation of pruning techniques. Pruning involves eliminating redundant or non-critical weights and neurons from a neural network without significantly affecting its performance. This compression reduces the number of necessary computations and, subsequently, the energy consumption associated with network operation. There are multiple methods of pruning, ranging from magnitude-based pruning, which removes weights with the smallest values, to more complex schemes that consider the structure and connectivity of the network. Quantization is another strategy used to improve neural network efficiency. It reduces the precision of the network's parameters from floating-point representations to lower bit width integers. This not only requires less memory for storage, but also speeds up inference by leveraging integer arithmetic, which commonly consumes less power than floating-point operations. The challenge with quantization is maintaining the accuracy of the network, and sophisticated techniques involve fine-tuning the quantized network to preserve its performance. Knowledge distillation is a technique where a smaller, more efficient student network is trained to mimic the behavior of a larger, high-performing teacher network. This process involves transferring the knowledge from the teacher to the student, often achieving comparable accuracy with a fraction of the computational resources. The student network can then be used in place of the larger network, leading to more resource-efficient deployment. Another important aspect of energy-efficient design is the architecture of the neural network itself. Custom architectures, such as mobile nets and efficient nets, have been specifically created to provide optimal performance under resource constraints. These models feature architecture adjustments, such as depth-wise separable convolutions, which require fewer calculations than standard convolutions. Such designs often take into account not only the computational cost, but also the memory footprint, achieving a balance that is crucial for deployment on resource-limited platforms. The utilization of advanced hardware is also critical in achieving efficient neural network execution. Specialized hardware such as field programmable gate arrays, FPGAs, application-specific integrated circuits, ASICs, and graphics processing units, GPUs, can be optimized for the operations that neural networks require. These often include parallel processing capabilities, which can dramatically increase efficiency compared to general-purpose processors, especially for tasks such as convolutional operations in neural networks. Software optimization is an equally important component of an efficient neural network. This involves optimizing the algorithms and routines used for both training and inference phases. Software frameworks can be optimized at a low level to make the most of the underlying hardware's capabilities, such as leveraging vectorized operations and cache optimizations. In addition, efficient use of data formats and optimized memory access patterns further reduce resource consumption. Data efficiency complements architectural and algorithmic efficiency. It focuses on the informational content of the data used for training neural networks. Techniques such as data augmentation and selective sampling can ensure that the model learns efficiently from the most informative examples, requiring fewer epochs to converge, and thus reducing the overall energy consumption required for training. Another facet of resource efficiency is scalability. Efficiently designed neural networks should be able to scale across different hardware platforms without a significant loss in performance. This means that a model trained on high-powered GPU clusters should also work effectively when deployed on single GPUs or even CPUs in edge devices. Designing for scalability involves considering hardware variability and optimizing networks to adapt to these differences while maintaining efficiency. There is also increasing interest in algorithms that promote sparse representations and computations in neural networks. Sparsity refers to the natural zeros in data or model parameters which, when exploited, can reduce the number of computations and memory usage. Novel training algorithms can encourage sparsity within network weights or activations, directly translating to efficiency gains during both training and inference. Finally, a holistic approach to energy and resource-efficient neural network design involves life cycle considerations. From the initial training to the ongoing maintenance and eventual decommissioning of models, each stage should be optimized for efficiency. This approach includes creating models that require less frequent retraining, implementing incremental learning strategies, and ensuring that models remain accurate and relevant without substantial additional computational investment over time. The design of energy and resource-efficient neural networks is a multifaceted problem that intertwines hardware, software, and algorithmic advances. It requires a deep understanding of the trade-offs between computational resources and model performance. Given the current computation-intensive trend in artificial intelligence, efforts in this direction are necessary not only for environmental sustainability, but also for the continued proliferation of machine learning applications in the real world. 8.9 Neural networks in distributed computing environments. Neural networks have seen a significant increase in complexity and size, leading to challenges in computational resources and efficiency. With the advent of big data and an ever-increasing need for computational power, traditional single-machine setups are often insufficient for training these models. Distributed computing environments offer a solution by allowing neural network training processes to be spread across multiple computing units. This approach takes advantage of parallel processing capabilities, distributing the workload across clusters of computers, often located in different geographic regions. A distributed computing environment in the context of neural networks involves splitting the model's data and computations across servers or devices. This can reduce training time considerably by handling computations and parameter updates in parallel. For instance, when training a large-scale deep learning model, a dataset can be partitioned into batches distributed to multiple processors. Each processor then performs forward and backward passes on its batch of data and computes gradients for the model's parameters. These gradients are then aggregated to update the model weights, a process often managed by parameter servers or through collective operations. Data parallelism and model parallelism are two primary strategies used in distributed neural network training. In data parallelism, the entire model is replicated across multiple processors, and each processor works on a different subset of the data. In contrast, model parallelism involves distributing the model's architecture across different processors, with each processor responsible for a portion of the network. While data parallelism is ideal for scenarios where the model fits into the memory of each processor, model parallelism is useful for larger models that exceed the memory capacity of a single processing unit. The synchronization of updates to the model parameters is a critical element of successful distributed training. Typically, this is handled by either synchronous or asynchronous update mechanisms. Synchronous updates, while ensuring consistency, can lead to idle time since all nodes must wait for the slowest one before proceeding to the next iteration. Asynchronous updates can alleviate this bottleneck by allowing nodes to update independently on their schedule. However, asynchronous updates can introduce challenges with convergence and require careful tuning to maintain model quality. Efficiency in distributed computing for neural networks is also influenced by the network topology and bandwidth available between the processing units. High-performance interconnects are crucial to reduce communication overhead, especially when frequent parameter updates are necessary. The choice of a distributed system framework can substantially impact the ease of setup and the scalability of the training process. Frameworks such as TensorFlow, PyTorch, and Apache MXNet provide built-in support for distributed computing, offering various tools and features to simplify and optimize distributed training. Another area of consideration for optimization is the partitioning strategy implemented before training begins. Deciding how to split the model and data across the available nodes can have significant performance implications. For example, poorly balanced data distribution can result in some nodes being underutilized. Optimal distribution strategies aim to ensure each computing unit has a proportional workload, thereby improving overall system efficiency. Load balancing becomes increasingly important in heterogeneous distributed environments where the computing nodes may have different capabilities. In these settings, tasks must be assigned not just by split evenness, but by the computation and communication capabilities of each node. Advanced load balancing techniques take into account the current workload, memory usage, and network bandwidth of each node to dynamically redistribute tasks as conditions change. Fault tolerance is another essential factor to consider in distributed neural network training. Challenges such as network instability, hardware failures, or power outages must be addressed to prevent loss of progress or data. Checkpointing, a process of saving the state of the model periodically, enables training to resume from the last saved state in case of failure rather than starting from scratch. Some distributed computing frameworks offer automated checkpointing and recovery features, which are invaluable for long-running training processes. Another essential aspect of distributed systems is the overall security of the training data and the model. Ensuring secure communications between nodes and protecting sensitive data from unauthorized access should be paramount due to the distributed nature of the setup. Appropriate encryption methods for data in transit and robust authentication mechanisms for nodes entering the computing cluster are necessary to maintain the integrity of the model and data. Monitoring and managing distributed training sessions are also crucial for maintaining efficiency. Administrators and practitioners must have tools to visualize and analyze system performance, including computation and communication metrics. These insights help identify bottlenecks, imbalances, or inefficiencies, enabling continuous adjustments to the training procedure and infrastructure. In summary, distributed computing environments offer powerful solutions to the challenges of training large neural network models. By leveraging multiple computational units in a coordinated manner, practitioners can significantly reduce training times and manage the resource demands of complex models. However, distributed training requires careful attention to synchronization, data and model partitioning, load balancing, fault tolerance, security, and system monitoring to ensure optimal efficiency and effectiveness. With the right approach and tools, distributed neural network training can push the boundaries of what is possible in machine learning applications. 8.10 Monitoring and Maintenance of Neural Network Systems. The monitoring and maintenance of neural network systems are critical processes that ensure these systems remain functional, efficient, and accurate over time. Effective maintenance strategies can lead to prolonged system life, better performance, and reduced costs associated with downtime or catastrophic failures. The high complexity of neural networks, coupled with their dynamic environments, mandates a structured approach to their maintenance. This entails regular inspections, updates to reflect new data or changing conditions, and continuous monitoring of their performance metrics. Monitoring a neural network involves vigilance over its operational parameters, which typically includes assessing the accuracy of its outputs, the efficiency of its computational processes, and the relevance of its learned parameters to the current data environment. Metrics such as precision, recall, and F1 score are commonly used for evaluating classification tasks, while mean squared error or mean absolute error may be adopted for regression tasks. Additionally, hardware performance metrics like processing speed, memory usage, and energy consumption are also tracked to ensure the infrastructure supporting the neural network remains robust and capable. Maintenance activities are performed in accordance with the insights gleaned from the monitoring process. These can include retraining the network with new data to prevent model decay, pruning redundant or non-informative connections to improve efficiency, or executing software patches to address security vulnerabilities. Retraining is particularly important in fields where data distributions change over time, such as fraud detection or recommendation systems, where new user behaviors and preferences must be captured regularly. The process of retraining involves several stages. Firstly, the new data must be collected, pre-processed, and validated to ensure consistency and quality. Following this, the data is fed into the network either incrementally or in batch mode, depending on the nature of the system and its learning algorithm. It is crucial that this process does not introduce bias or skew the network's learned representations. During retraining, a balance must be struck between maintaining previously learned useful knowledge, often called catastrophic forgetting, and updating the model to reflect new insights. Pruning is another maintenance technique for optimizing neural networks. By removing neurons or connections that contribute little to the network's output, computational efficiency can be improved without significantly impacting performance. This process can be guided by analyzing neuron activation patterns and weights, with less active or lower weight connections being prime candidates for elimination. Pruning also helps in reducing the model size, leading to less memory consumption, and sometimes better generalization by removing some overfitting artifacts. Deployed neural networks necessitate robust mechanisms to handle anomalies and errors. Monitoring tools must include the ability to detect and alert on anomalous behavior that could indicate a problem with the network. This could range from data input issues to hardware failures. Anomaly detection is often implemented using statistical methods or secondary machine learning models trained to recognize signs of malfunction. Regular software updates are imperative for maintaining the security and efficiency of neural networks. As vulnerabilities are discovered and new optimization techniques are developed, updating the software that manages neural network operations ensures protection against threats and improved performance. Any update process should be carefully managed to prevent disruption, with changes thoroughly tested before deployment into a production environment. Documentation throughout the life cycle of a neural network is essential for effective monitoring and maintenance. Keeping records of the network's architecture, configurations, training data, and changes over time facilitates easier diagnosis of issues and more efficient collaboration among team members. Clear documentation is particularly useful when transferring maintenance responsibilities or scaling up operations. Performance benchmarks play a vital role in maintenance as well. By periodically comparing the neural network's performance against predetermined thresholds or targets, maintainers can identify when action is needed. These benchmarks should reflect both the original objectives of the system and any evolving requirements that may arise due to changes in its operating context. Despite automation's increasing role in system maintenance, human expertise remains irreplaceable. Experienced data scientists and engineers are pivotal in interpreting complex patterns in performance data, making judgment calls when unforeseen circumstances arise, and providing a nuanced understanding of how various factors affect a neural network's functioning. Their insights guide the strategic decisions related to network modification and the prioritization of maintenance tasks. As neural network systems become more integral to a wide array of applications, the sophistication of monitoring and maintenance strategies must evolve correspondingly. This includes employing advanced techniques such as predictive maintenance, where machine learning models are used to anticipate failures or performance drops before they occur. Furthermore, integrating continuous integration, continuous deployment, CI/CD pipelines for neural networks can streamline the update and retraining process, enabling a more agile response to emerging requirements or issues. The longevity and success of neural network deployments hinge on an effective monitoring and maintenance strategy. A comprehensive approach encompasses performance measurement, swift responses to identified issues, and informed updates, all undergirded by thorough documentation and the irreplaceable acumen of skilled professionals. As neural networks transform more sectors, the ability to maintain these complex systems efficiently will be a competitive advantage and a mark of technical excellence.